Hello everyone, welcome back to the channel. Today we are going to explore one of the most successful and fascinating theories ever created in science, quantum electrodynamics, often called QED. This theory describes how light and matter interact at the smallest scales we can measure, and it stands as one of the most precise theories in human history. To understand why QED is so important, we first need to think about two great pillars of physics: quantum mechanics, which explains the behavior of very small particles like electrons and photons, and electromagnetism, which explains how electric charges and magnetic fields interact. For many years, these two areas existed as separate ideas. Scientists could describe how light behaves and how charged particles move, but combining these ideas into one complete picture was extremely difficult. QED is the theory that finally succeeded in merging them into a single, consistent framework. At its heart, quantum electrodynamics explains how electrically charged particles such as electrons and positrons interact with light, which is made of particles called photons. In everyday life, we think of light as a wave and electricity as something that flows through wires. But at the quantum level, everything becomes discrete and probabilistic. Instead of smooth, continuous interactions, particles exchange energy in tiny packets. QED tells us that when two charged particles interact, they do so by exchanging photons. These photons are not always visible light. Many of them are virtual photons that exist only briefly during the interaction and cannot be directly observed. These exchanges determine forces, energy transfer, and even the structure of atoms. The road to QED was not easy. Early quantum theory explained the structure of atoms and why electrons occupy specific energy levels, but it could not fully explain how light interacts with matter in a consistent relativistic way. When scientists tried to calculate certain physical quantities, they often obtained infinite results, which made no physical sense. For example, when calculating the self-energy of an electron, the equations suggested that the electron's energy would be infinite due to its interaction with its own electromagnetic field. Clearly, this could not be correct, because real electrons have finite energy and mass. This problem troubled physicists for many years and suggested that the theory was incomplete or poorly understood. The breakthrough came in the middle of the 20th century when several physicists independently developed new mathematical tools to handle these infinities and make sense of the equations. One of the most influential figures in this story was Richard Feynman, who introduced a new way of visualizing and calculating particle interactions using simple diagrams that now bear his name. These diagrams represent particles as lines and their interactions as points where lines meet. While the diagrams look simple, they encode complex mathematical expressions that allow physicists to calculate probabilities of different physical processes. With these tools, it became possible to calculate observable quantities, such as the scattering of electrons or the emission of light, with extraordinary accuracy. To understand QED conceptually, imagine an electron moving through space. According to classical physics, it carries an electric charge and creates an electric field around it. In QED, this picture is refined. The electron is constantly interacting with the quantum electromagnetic field, emitting and absorbing photons. These photons mediate the electromagnetic force. When two electrons repel each other, what is really happening is that they are exchanging virtual photons. These photons carry momentum and energy, and this exchange results in a force that pushes the electrons apart. Similarly, when an electron is attracted to a positively charged proton in an atom, the attraction is again explained by the exchange of photons. One of the most remarkable aspects of QED is its predictive power. For example, it predicts the value of the electron's magnetic moment with extraordinary precision. The magnetic moment is a property of the electron related to how it behaves in a magnetic field. Classical physics predicts a certain value, but QED shows that the electron's interaction with the quantum vacuum slightly modifies this value. These tiny corrections arise from processes in which the electron emits and reabsorbs photons, or briefly transforms into other particles and then returns to being an electron. When scientists measure the electron's magnetic moment experimentally, the result matches the QED prediction to more than 10 decimal places. This agreement between theory and experiment is one of the strongest confirmations of any scientific theory ever created. To see why QED works so well, we need to talk about the idea of quantum fields. In classical physics, fields such as the electric field and magnetic field are smooth quantities defined at every point in space. In quantum field theory, these fields become operators that can create and destroy particles. The electromagnetic field is quantized, meaning that its excitations are photons. Similarly, the electron is described by its own quantum field, and interactions occur when these fields couple to each other. QED is the quantum field theory of the electromagnetic interaction. It describes how the electron field interacts with the electromagnetic field, and from this interaction, all electromagnetic phenomena emerge. A key concept in QED is probability amplitude. Instead of predicting exactly what will happen in a given interaction, QED assigns a probability to each possible outcome. These probabilities are obtained by calculating complex numbers called amplitudes and then taking their absolute squares. This approach reflects the fundamentally probabilistic nature of quantum mechanics. When an electron scatters off another electron, there are many possible paths the interaction could take, including different ways of exchanging photons. QED tells us how to calculate the amplitude for each of these possibilities and how to combine them to obtain the total probability of a given outcome. Another important idea is the vacuum. In everyday language, we think of a vacuum as empty space with nothing in it. In QED, the vacuum is not empty at all. It is filled with fluctuating fields and virtual particles that appear and disappear constantly. These fluctuations have measurable effects. For instance, they modify the electric charge of particles and influence how forces behave at very short distances. This is why the charge of an electron depends slightly on the energy scale at which it is measured. At higher energies, the electron appears to have a different effective charge because the surrounding cloud of virtual particles changes how its field spreads through space. The problem of infinities, which plagued early attempts at quantum field theory, was solved using a procedure called renormalization. Renormalization involves redefining certain physical quantities, such as mass and charge, in a way that absorbs the infinities into these definitions. Although this may sound like a mathematical trick, it has deep physical meaning. It reflects the fact that what we call the mass and charge of a particle already include the effects of its interaction with the quantum vacuum. When this is taken into account consistently, the theory yields finite, meaningful results that can be compared with experiments. To appreciate how QED works in practice, consider a simple example: the scattering of two electrons. According to QED, the simplest process involves one electron emitting a virtual photon, which is then absorbed by the other electron. This single exchange accounts for the basic repulsive force between them. More complicated processes involve the exchange of multiple photons or the creation and annihilation of particle-antiparticle pairs during the interaction. Each of these processes contributes a small correction to the total probability. By adding up all these contributions, physicists obtain a result that can be tested experimentally. The more precise the experiment, the more of these corrections must be included in the calculation. One of the most profound insights of QED is that interactions are not continuous in time but occur through discrete events. These events are represented mathematically by interaction terms in the theory's equations and visually by points in Feynman diagrams. Between these interactions, particles propagate freely according to quantum mechanics and relativity. This picture provides a clear and intuitive way of thinking about complex quantum processes, even though the underlying mathematics is highly sophisticated. QED also plays a central role in our understanding of atoms and molecules. The structure of atoms is determined by the electromagnetic interaction between electrons and the nucleus. QED provides corrections to the simple picture given by non-relativistic quantum mechanics. For example, it explains the fine structure of atomic spectra, which arises from relativistic effects and the interaction between the electron's spin and its orbital motion. It also explains the Lamb shift, a small difference in energy between two atomic states that were predicted to be identical by earlier theories. This shift arises from the interaction between the electron and the vacuum fluctuations of the electromagnetic field. In addition to explaining known phenomena, QED has influenced the development of other theories. It served as a model for constructing quantum field theories of the other fundamental forces. The techniques developed for QED, such as renormalization and diagrammatic methods, were later applied to the weak and strong nuclear forces, leading to the standard model of particle physics. In this sense, QED is not only a theory of light and matter, but also a foundation for much of modern theoretical physics. The philosophical implications of QED are also worth considering. It challenges our classical intuitions about space, time, and causality. In QED, particles do not have well-defined trajectories like tiny billiard balls. Instead, their behavior is described by probability amplitudes that spread out over space and time. Interactions are not simple pushes or pulls, but exchanges of virtual particles that cannot be directly observed. This picture is deeply counterintuitive, yet it is supported by countless experiments. It suggests that reality at its most fundamental level is governed by mathematical structures and probabilities, rather than by deterministic laws in the classical sense. Despite its success, QED is not the final theory of everything. It describes only the electromagnetic interaction and does not include gravity. At very high energies, new physics may appear that goes beyond QED. Nevertheless, within its domain of applicability, QED remains unmatched in precision and reliability. It provides a clear example of how abstract mathematics can lead to concrete predictions about the physical world, predictions that can be tested and confirmed to astonishing accuracy. When teaching or explaining QED, it is important to emphasize not only the technical results but also the way of thinking it represents. It shows that complex phenomena can be understood by breaking them down into simpler interactions, and by carefully accounting for all possible contributions. It also shows the importance of consistency between theory and experiment. The history of QED is a story of persistent effort to reconcile elegant mathematical ideas with stubborn experimental facts. Each time a discrepancy appeared, physicists refined their understanding and improved their calculations until the theory matched reality. In everyday technology, QED may seem distant, but its influence is everywhere. The behavior of semiconductors, lasers, and many electronic devices depends on the interaction between electrons and electromagnetic fields at the quantum level. While engineers do not usually solve full QED equations when designing devices, the principles underlying these technologies are rooted in the same physics. In this way, QED connects the abstract world of theoretical physics with the practical world of modern technology. As we reflect on quantum electrodynamics, we see a theory that unites deep mathematical structure with physical insight. It teaches us that even the simplest phenomena, like the attraction between two charges or the emission of light from an atom, arise from a rich and subtle interplay of quantum fields. It reminds us that the universe is not only stranger than we imagine, but stranger than we can imagine, yet still accessible through careful reasoning and experiment. QED stands as a monument to human curiosity and ingenuity, showing how far we can go by asking the right questions and refusing to accept easy answers. Quantum electrodynamics also introduced a new way of thinking about cause and effect at the microscopic level. In classical physics, one event clearly causes another in a straightforward sequence. In QED, however, interactions are described as sums over all possible processes that could lead from an initial state to a final state. This means that nature does not commit to a single path or mechanism. Instead, every allowed path contributes to the final outcome, and what we observe is the result of interference between all these possibilities. Some paths reinforce each other, while others cancel out. This idea, although strange, is essential for understanding how QED makes its predictions. The mathematical core of QED is built on relativistic quantum mechanics, meaning it respects the principles of Einstein's special relativity. This is crucial because electromagnetic interactions propagate at the speed of light, and any correct theory must treat space and time on equal footing. QED achieves this by using equations that are consistent with relativity, such as the Dirac equation for electrons and a quantized version of Maxwell's equations for the electromagnetic field. When these equations are combined, they describe how charged particles move and how they emit and absorb photons in a way that does not violate the fundamental speed limit of the universe. One of the most powerful ideas introduced into QED is the concept of perturbation theory. Because the electromagnetic interaction is relatively weak compared to some other forces, physicists can treat it as a small correction to simpler systems. They begin with a situation they can solve exactly, such as a free electron, and then add the interaction as a small disturbance. Each level of approximation corresponds to processes with increasing numbers of photon exchanges and particle loops. The simplest approximation gives the dominant effect, while higher-order terms provide tiny corrections. This method allows calculations to be organized systematically and makes it possible to achieve very high precision when enough terms are included. These higher-order terms often involve so-called loop diagrams, where a particle emits and reabsorbs a photon or briefly turns into a particle-antiparticle pair. These loops represent the influence of the quantum vacuum and the fact that particles are never truly isolated. They are always interacting with the surrounding fields, even in empty space. Although each loop contributes only a small amount, their cumulative effect can be measured in experiments. This is why QED can explain small deviations from classical predictions, such as the anomalous magnetic moment of the electron and subtle shifts in atomic energy levels. The idea that empty space is full of activity is one of the most striking lessons of QED. Virtual particles constantly appear and disappear, borrowing energy for short periods in accordance with the uncertainty principle. These fluctuations affect the propagation of light and the behavior of charges. For example, when a photon travels through the vacuum, it can briefly turn into an electron-positron pair, and then recombine into a photon. This process slightly alters the way light moves through space, and contributes to effects such as vacuum polarization. These phenomena are not just theoretical curiosities, they have been confirmed through precise measurements in laboratories. Another remarkable feature of QED is gauge symmetry. The theory is built so that certain transformations of the electromagnetic field leave the physical predictions unchanged. This symmetry is not just a mathematical convenience, it reflects a deep principle about the redundancy in our description of nature. Gauge symmetry ensures the conservation of electric charge and dictates the form of the interaction between electrons and photons. In QED, the requirement of gauge symmetry uniquely determines how the electromagnetic field couples to charged particles. This idea later became central in constructing theories of the other fundamental forces. QED also teaches us something profound about the nature of measurement. In the quantum world, the act of observing a system influences its behavior. When we measure the position or energy of an electron, we are forcing it into a particular state, and the result is inherently probabilistic. QED does not predict exactly what will happen in a single experiment, but provides probabilities for different outcomes. When the same experiment is repeated many times, these probabilities reveal themselves as stable patterns that can be compared with theoretical predictions. This statistical nature of prediction is not a limitation of the theory, but a reflection of how nature behaves at small scales. The experimental confirmation of QED is one of the greatest triumphs in science. Experiments involving the scattering of electrons and photons, the behavior of atoms in magnetic fields, and the precise measurement of spectral lines all agree with QED's predictions. Perhaps the most famous example is the measurement of the electron's anomalous magnetic moment. This quantity has been measured with astonishing precision, and the theoretical value calculated from QED matches it to more than 10 significant figures. Such agreement is almost unheard of in other areas of physics, and demonstrates the extraordinary accuracy of the theory. It is important to remember that this precision did not come easily. Early calculations were extremely difficult and required new mathematical techniques and powerful computers. Physicists had to carefully account for many tiny effects and ensure that their approximations were valid. The success of these efforts showed that quantum field theory could be a reliable framework for describing nature, not just a collection of abstract ideas. QED became a testing ground for methods that would later be used to study the strong and weak nuclear forces. Beyond its technical achievements, QED also changed the culture of physics. It emphasized the importance of clear physical interpretation alongside mathematical rigor. One of the reasons the theory became so influential is that it provided intuitive pictures of complex processes through diagrammatic representations. These pictures help physicists think creatively about interactions and identify which contributions were most important. They also made it easier to communicate ideas and collaborate across different areas of research. The role of Richard Feynman in this transformation cannot be overstated. His approach combined deep physical insight with a playful curiosity about how nature works. He believed that understanding a theory meant being able to explain it in simple terms and to see how it applied to real phenomena. His work on QED exemplified this philosophy, turning a set of abstract equations into a practical tool for calculating measurable quantities. This style of thinking continues to influence how physics is taught and practiced today. QED also raises deep questions about the limits of scientific knowledge. Because it relies on probabilities and virtual processes that cannot be directly observed, it challenges our classical notions of reality. What does it mean to say that a virtual photon exists if it can never be detected? How should we interpret processes that violate ordinary ideas of cause and effect over very short times? These questions do not undermine the theory's success, but they remind us that our descriptions of nature are models that capture certain aspects of reality while leaving others mysterious. In modern physics, QED is seen as part of a larger framework known as the Standard Model, which includes theories of the weak and strong nuclear forces. Within this framework, QED describes the electromagnetic interaction, which governs the behavior of charged particles and light. The same principles of gauge symmetry and quantum fields that underlie QED also apply to these other forces, although the details are more complex. In this sense, QED serves as a prototype for understanding how fundamental interactions can be described in a unified way. The influence of QED extends beyond particle physics into other fields such as condensed matter physics and astrophysics. In solids, electrons interact with electromagnetic fields and with each other in ways that can often be described using techniques inspired by QED. Phenomena such as superconductivity and the quantum Hall effect involve collective behavior of electrons that reflects the underlying quantum field nature of matter. In astrophysics, QED effects become important in extreme environments, such as near neutron stars, where magnetic fields are so strong that they modify the behavior of the vacuum itself. Teaching QED is a challenge because it combines abstract mathematics with counterintuitive concepts. However, its core ideas can be conveyed in simple terms. Particles interact by exchanging other particles. Probabilities replace certainties. And even empty space plays an active role in physical processes. These ideas can be illustrated with examples from atomic physics, optics, and everyday technology, helping students see how a deep theory connects with familiar experiences. Another important lesson of QED is the role of approximation in science. No calculation in QED includes all possible contributions exactly, because there are infinitely many of them. Instead, physicists include as many terms as needed to achieve the desired level of accuracy. This shows that scientific knowledge is often a matter of degree rather than absolute certainty. We do not need perfect knowledge of every detail to make reliable predictions. We need only enough information to describe phenomena within the limits of experimental precision. The story of QED also illustrates how theoretical and experimental physics work together. Experimental discoveries such as the Lamb shift revealed discrepancies with existing theories and forced physicists to develop better models. Theoretical advances, in turn, suggested new experiments and measurements. This feedback loop between theory and experiment is essential to scientific progress and is beautifully demonstrated in the history of QED. From a broader perspective, QED shows how the universe can be understood in terms of simple underlying principles. The interaction between light and matter, which appears so complex in everyday life, can be traced back to a few basic rules governing quantum fields. These rules are expressed mathematically, but they also have clear physical meaning. They tell us that particles are excitations of fields, that forces arise from the exchange of quanta, and that probabilities are fundamental to nature. At the same time, QED reminds us that our understanding is always provisional. While it is extremely accurate, it is not complete. It does not explain why the fundamental constants of nature have the values they do, nor does it incorporate gravity. Physicists continue to search for deeper theories that will unify all interactions and explain the origin of the laws we observe. In this ongoing quest, QED stands as a benchmark for what a successful physical theory can achieve. The practical applications of QED may not be obvious, but its concepts underpin much of modern technology. The design of lasers, the operation of transistors, and the behavior of materials at the nanoscale all rely on quantum principles that are closely related to those of QED. While engineers use simplified models rather than full quantum field theory, the validity of these models rests on the deeper theoretical framework provided by QED. As we continue to explore the universe at both the smallest and largest scales, QED remains a central part of our intellectual toolkit. It provides a precise and consistent description of one of the fundamental interactions, and offers insights into the structure of matter and the nature of light. Its success gives us confidence that the language of quantum fields is a powerful way to describe reality, even if it challenges our intuitions. Quantum electrodynamics is therefore more than just a set of equations. It is a way of thinking about the world, a method for connecting abstract ideas with concrete observations. It shows how careful reasoning, guided by experiment, can reveal hidden layers of reality. It also shows that the universe, despite its complexity, can be understood through a combination of imagination, mathematics, and empirical evidence.